In this video, we're going to use two different ways to solve the Pythagorean Theorem proof. So we're going to start by taking a look at a triangle with A, B, and C for the lengths. And we'll actually take a look at four triangles. Each triangle is the same length of A, B, and C. We'll color code it to make it a little bit easier to see. So what we're going to do is rotate these four triangles so that we can actually create a square that you see right here. Now, if you remember that each one of these sides of these triangles has either A or B or C, which we can put here. And you'll notice that we actually have a smaller square that's tilted sideways, which is going to be C times C. So the area inside of it is going to be C squared. So we'll make that area white. And let's say we have a same square that's the same size, but this time what we're going to do is rotate those triangles in a different orientation. So remember again, we have A, we have B for these sides. We have A and we have B for these sides. Well, now we have an area of B squared, which is here. We have an area of A squared, which is here. Now this area of white is the same for the C squared as it is for this other giant square that we see here. It's just that we orientated the triangles in different directions. So that would give us that A squared plus B squared, the white area inside of this triangle, is the same as the white area inside of this square, which we see is going to be C squared. So that would be our proof for Pythagorean theorem. Now there's another way that we can solve for this proof. We can take a look at a triangle that has points A, B, and C. Not the sides, but actually at the end points here. And if we set a line that is perpendicular from the hypotenuse across to A, and we have a right angle here, we can actually look at three triangles that are going to be similar in shape, but they're going to just have different sizes, meaning that the angle here is the same angle as here and here. And we can use this information to make comparisons. So for instance, we know that this side length is similar to this side length. So we can say that AC over CD is equal to the hypotenuse of this one to the hypotenuse of this one. So that would be BC over AC. And that's also similar to, say, this triangle that has a length here to our biggest triangle, which has a length here. So that would be AB over BD. And that would be similar to the hypotenuse of our big one to our middle one here, which is going to be BC over AB. So if we cross multiply these two equations, what we can end up seeing is something to help us solve this proof. So AC times AC would give us AC squared, and that's equal to BC times CD. And also, we would have AB squared is equal to BC times BD. Now we can use this information to help us solve for Pythagorean theorem. We know that the length of A to C would be the same as the length of A, and we know that the length of A to B would be similar to the length of B. Well, if we see that we have A squared and we have B squared here, that can help us to say that A squared plus B squared would be equal to what's on the other side of A squared, which is equal to BC times CD, plus what's on the other side of B squared, which is equal to BC times BD. We can factor out a BC here, so we'd have CD plus BD. Well, we know that from B to C would give us C, and that we have a length of C to D plus a length of B to D would be another full length of C. So that would give us C times C, which is equal to C squared. So that would give us that A squared plus B squared is equal to C squared.